Hi students, this is the first educational video among a series of tutorials showing how to determine the normal force, the shear force, and the bending moment diagrams for a loaded frame. Of course, I'll explain this as simply and as clearly as possible. Okay, let's go. Well, for our problem description, let's consider a simple frame ABCD as it is depicted by this slide. This frame is constituted, of course, by left-hand and right-hand columns as vertical elements and a beam as horizontal element. The height h of this frame is equal to 4 meters and the span s is equal to 7 meters. This frame is supported by a pennant support at the bottom of the left-hand column at the point A and by a roller support at the bottom of the right-hand column at the point D. This frame is also loaded by uniformly distributed load UDL equal to 4 kilonewtons per meter. The frame analysis consists in 5 steps. The first one is the checking of the determinacy. The second step is the determination of reactions at the points A, B, C, and D. The third step is the drawing of the normal force diagram for columns and beam. The fourth step is the drawing of the shear force diagram for columns and beam. And the fifth step is the drawing of bending moment diagram for columns and beam. Now I'll try to explain the determinacy checking. So we have our frame ABCD supported by a pennant support at the point A and a roller support at the point D. And let's consider M the number of members, R the number of support reactions, J the number of joints, and C the equations of condition, which is equal to 1 equation for each internal pin and 2 equations for one internal roller. So, of course, we have 2 columns and 1 beam, so we have a number of members M equal to 3. For the number of support reactions, we have a vertical and horizontal reactions at the point A, since it is a pin support, and we have one single vertical reaction at the point D since it is a roller support. So the number of support reactions R is equal to 3. For the number of joints, we have 4 joints at the point A, B, C, and D. So the number of joints J is equal to 4. And for C, the equations of condition, we have nor internal pin, neither internal roller. So the equation of condition C is equal to 0. Well, for the determinacy checking, we have 3 cases. The first one is when 3m plus r is equal to 3j plus c, and in this case, the structure is considered statically determinate. This means that all the unknown external reactions can be determined using only the static equilibrium equations without any need to additional equations such as compatibility equations. The second case is when 3m plus r is higher than 3j plus c. In this case, the structure is considered statically indeterminate, and this means that the determination of unknown external reactions need both static equilibrium equations and compatibility equations. For these 2 cases, the structure is considered stable, which means that the structure is able to maintain its geometrical shape under the external loading. The third case is when 3m plus r is lower than 3j plus c, and in this case the structure or the frame is considered statically unstable. Unstable means, as I explained, that the frame will be not able to maintain its geometry shape under the external loading. Well, for our case, we have 3m plus r is equal to 12 and 3j plus c is equal to 12. So we are in the case 3m plus r is equal to 3j plus c. So our frame is statically determinate and all the unknown external reactions can be determined using only the static equilibrium equations without any need to other additional equations. So our frame is statically determinate, and this justifies why we used a pennant support together with a roller support. Well, now I'll explain how to determine the external reactions applied on our loaded frame. First, let's convert the uniformly distributed load into a simple point load with a magnitude UDL multiplied by the span and applied at the half span at the point I, located at 3.5 meters from the point B. And let's consider the two directions x and y. X is the horizontal direction and y is the vertical direction. So in the pennant support we have the reaction at A along x and the reaction at A along y. And in the roller support we have a single reaction along the y direction denoted simply by RD. Now, in order to avoid complications when determining the reactions, we will use the static equilibrium equations of moment at the point A in order to neutralize RAX and RAY in order to determine directly the reaction RD. So when we apply the static equilibrium equations along y, we will obtain finally a reaction RD equal to the half span multiplied by the UDL, which will give finally 14 kilonewton. Now, in order to determine the reaction RAX, we will apply the static equilibrium equations of forces along x, and we will finally find that this reaction is zero. So we have not a reaction at A along x. And in order to determine the reaction at A along y, we have to apply the static equilibrium equations of forces along y, and we will find finally that the reaction RAY will be equal to the span multiplied by the UDL minus the reaction at the point D, which will give finally 14 kilonewton. Now I'll explain how to determine the normal force diagram associated to our frame. First, we explode our frame into a free body diagram, and we have the external forces applied on the columns and on the beam. In order to maintain equilibrium in the columns, we have to neutralize the 14 kilonewton applied at the bottom of the columns as normal force by another 14 kilonewton applied at the top of the column as normal force, but in the opposite direction. The 14 kilonewton applied at the top of the left-hand column as normal force will be transferred to the left-hand edge of the beam as shear force. And in the right-hand edge of the beam, the force will be the 14 kilonewton applied at the left-hand edge of the beam minus the UDL 4 kilonewton per meter multiplied by the span 7 meter, which will give finally minus 14 kilonewton. The normal force diagram will be determined based on the forces applied on the columns and on the beam. So it is clear that the columns are subjected to a compression, which is a normal force equal to 14 kilonewton in the opposite direction of y. So we will have minus 14 kilonewton at the left hand column as normal force, and same thing for the left hand column. So the normal force minus 14 kilonewton is applied along the two columns. You can notice also that for the beam we have only shear force, we have not normal force, so we have 0 kilonewton as normal force along the beam, and the normal force diagram associated to our frame will be as it is depicted in the left of this slide. Now I'll explain how to determine the shear force diagram associated to our frame. So we have our frame exploded into a free body diagram, and we have the external and internal forces applied on the columns and on the beam. And based on this, we will determine the shear force diagram. First, it's clear that the columns are not subjected to shear force, they are subjected only to normal forces, so the shear force along the column will be 0 kilonewton. Now for the beam, we have a shear force of 14 kilonewton applied at the left hand edge of the beam. This 14 kilonewton will be placed in the shear force diagram at the left hand edge of the beam. Same thing for the right hand edge of the beam. We have a shear force of minus 14 kilonewton, which will be placed here at the right hand edge of the beam. And based on the fact that the variation of the shear force along the longitudinal direction of the beam will be equal to minus the applied force, this 4 kilonewton per meter will be the slope of the variation of the shear force along the beam. We can determine also where on the beam the shear force will be equal to 0 by applying the equation of the line indicating the variation of the shear force along the beam, and we will find finally that the shear force will be equal to 0 at the midspan, which is x equal to 3.5 meter. Now for the bending moment diagram, it's obtained based on the shear force diagram, since the variation of the bending moment along the longitudinal direction of the element is equal to the shear force. You can notice that we have 0 kilonewton as shear force for the left hand and the right hand columns, so the bending moment will be constant or 0. Taking into consideration that we have a pennant support and a roller support at the bottom of the columns, we have so no resistance to rotation at the column's bottom, we can deduce that the bending moment diagram will be equal to 0 kilonewton meter along the left hand and the right hand columns. These 0 kilonewton meter as bending moment will be transferred from the column to the left hand and the right hand edge of the beam. Now, based on the area of the positive part of the shear force diagram, we can determine the maximum bending moment occurring at the half span where the shear force is equal to 0. The value of this maximum bending moment is equal to this area, since by definition the bending moment is the integral of the shear force. Even the variation of the bending moment along the beam is associated to the integral of the variation of the shear force along the beam. This educational video takes end. Please, if you have any remarks or suggestions, please mention it in the comments. Thank you very much for your attention.